Good morning, everyone. We're going to continue here this morning in chapter 11, talking about intermolecular forces. So this particular slide is looking at two molecules, one propanol. Of course, we know one propanol is where we have a hydroxyl group attached to the propane chain. And then acetic acid is, of course, a molecule we know the formula of as well, CH3COOH. Now, the difference between the two molecules is a slight difference in boiling point in that the acetic acid has a little bit of a higher boiling point. They both have comparable molecular weights. Whenever we're comparing intermolecular forces, I think it's better to compare compounds that have comparable molecular weights so that we can make a determination of what it is that's causing the difference in boiling points. If we had a massive difference in molecular weights, it could just be the added size of the bigger molecule that would give it a higher boiling point, but that's not the case here. In fact, with one propanol, you can kind of see how it has an internal hydrogen bond or an intermolecular hydrogen bond. That's the force that links the oxygen that has a hydrogen attached to it. And so then we're looking at the hydrogen interaction with the oxygen atom on another molecule. And so for hydrogen bonding, force of attraction, we have to have the H directly attached to NO or F. So we have H bonding in one propanol. We, of course, have a dipole-dipole force of attraction because we have a polar compound. And then we have dispersion forces too. In fact, with the one propanol, you can kind of see the dispersion force would be perhaps the chain of the molecule inducing a dipole moment in that part of the molecule. So maybe we have a little bit of an induced dipole moment going on in the chain of the molecule. So that's what we mean by having dispersion forces. So despite being polar, we can still have the molecule try to induce a bigger dipole moment through aligning its molecules and then shifting their electrons such that we pick up a change in charge. So maybe we're creating, a small dipole here in the chain of the molecule. And then the same thing with acetic acid. So acetic acid also has hydrogen directly attached to O. So we also have H bonding. So we have all of these same intermolecular forces as well for acetic acid, but the key detail is we pick up a second H bond. So just based on the fact that we have a bigger molecule, that we have two oxygens, we have this C double bond O to H group that helps form kind of like a ring structure where we pick up a second hydrogen bond simultaneously. And then that's the explanation for the higher boiling point, is that we just pick up that second hydrogen bond. Now, whether or not I would have expected you to predict that just looking at the structures of the molecule, I don't know. But seeing the structures overlaid on each other, seeing we only get one H bond here, and then here we get two H bonds. And we're also talking about why water had a higher boiling point than HF, despite HF having the greater electronegativity difference, is the fact water has two hydrogens and has the ability to form two hydrogen bonds. So having more hydrogen bonding abilities gives a substance a greater boiling point. Another compound that's commonly used that's related to alcohol or like ethanol is ethylene glycol. So ethylene glycol has a second hydroxyl group, so it's like alcohol plus an extra hydroxyl group. It's certainly not edible, so don't drink ethylene glycol. But ethylene glycol, we use it in our cars as a antifreeze. But the boiling point here is about 200 degrees C, because we now pick up the second hydrogen bonding site on the molecule. So we now have two hydrogen bond sites instead of just one on ethanol. So having two hydroxyl groups is better than having one. Having three would be even better. If you recall, on one of our previous examples last time had a glucose molecule that had a bunch of OH groups on the molecule. So we have a lot of hydrogen bonding sites on sugars. And that gives them a strong intermolecular force of attraction, therefore more energy to break those forces, so hence higher boiling points and melting points. I recall I skipped that previous slide to get to this slide here. So I guess we get to see the glucose again. So we have all these hydroxyl groups that give 1, 2, 3, 4, 5 different hydrogen bonding sites on a glucose molecule. So it can be interacting with other glucose molecules. So the key for intermolecular forces is it's not so much a property within one molecule, it's the ability that the molecule has to interact with a neighboring molecule through intermolecular forces. So glucose has the ability to interact with 5 different groups on different molecules, giving it a strong force of attraction. If you look at the melting point here, 150 degrees C, if you take roughly that same molecular weight, then have a straight chain hydrocarbon instead, so you lose all the hydrogen bonding sites but you still have a long molecule, so you still have a bunch of dispersion forces. Notice that the melting point drops to just 10 degrees C. So we lose most of our melting point here due to losing those hydrogen bonding sites. One interesting part of glucose is it doesn't melt and then boil like a normal compound. It decomposes, it kind of like caramelizes, instead of melting and then going through a normal boiling process. So you don't see a boiling point listed for glucose just because the compound just decomposes before it can boil. But we do see a pretty high boiling point for dodecane. So even though dodecane doesn't have any polarity to it, it's a nonpolar compound. And so we can see that through its dipole moment, it's close to 0. The CH bond's not very polar. All these bonds are opposing each other anyways. So we get no polarity here. So the only force we get is dispersion forces, but we have a bunch of atoms. And so having a lot of atoms gives a strong dispersion force. So imagine you have a second dodecane molecule. I'm not going to count those, but you can imagine if we had two molecules that we can induce a dipole moment across the chains of these molecules, and then in inducing the dipole moment, we're creating these partial charges, and then the same but opposite charges in the opposite molecule. So we're creating all these dipoles and creating a force of attraction between the two molecules that then has to be overcome to separate them. So having a longer chain of carbon atoms is better than having a shorter chain of carbon atoms. So if you think about methane, methane's a gas at room temperature because with just a single methane molecule, it's kind of like two spheres next to each other, pretty hard for that molecule to induce a dipole moment. But if you take 11 carbon atoms, I think that's 11 carbon atoms, maybe it's 12, whatever the count is, we could count if we cared. But we have a lot of carbon atoms, so we can induce that dipole moment to be great so that we have a relatively high boiling point, but not as high if we had hydrogen bonding. Then if we shorten the molecule to just have two atoms instead of all those atoms in dodecane, so instead of just having that mass across a big long molecule, we have it combined into two atoms. That's not great. Nonpolar compound, of course, we see still only the dispersion force of attraction, now a much lower boiling point due to having fewer atoms. And then if we go down to just having one atom, notice how low the boiling points are for our noble gases. So it's better to have two atoms instead of one for strong intermolecular forces with comparable molecular weights. And it's better to have 20 plus atoms than it is to have two atoms. So having more atoms spreads out the electrons in the molecule, makes the electrons easier to push around or to induce that dipole moment in the molecule. Okay, so this question here is getting back at something we talked about last time, which was about branching. And so having a branching point in a structure weakens intermolecular forces. And so why don't you guys think about this question here? Which molecule below likely has the greatest boiling point? So I may not give you enough time to fully think through a solution here, but the two things you might be thinking are the difference between having the hydroxyl group versus the NH2 group. And I'm kind of coming back to water versus NH3, and that water was the winner by a lot in boiling point because we have the more polar OH bond. Despite having 3 hydrogen bonding sites on ammonia, we've weakened the hydrogen bond such that it's not strong enough to overcome the difference of electronegativity. And so water kind of won the war, if you recall, just like it was forms a stronger force of attraction. So we're going to expect that the hydroxyl group forms the stronger intermolecular force and therefore is going to require more energy to separate. If I'm looking at my carbon chains, I have 1, 2, 3, 4, 5 carbon chains on these molecules. And then, so having the same chain of carbon atoms gives the same dispersion force. So the key is we get a more polar group with the hydroxyl group than we do with the ammonia group or with the NH2 group. And so that rolls out the NH2 compounds as being likely to have the highest boiling point. And then what about branching? So the one structure here has a branch point. What that means is the branch point kinks our structure in such a way that if we're picturing two of these molecules allayed next to each other, that this branching point here is going to make it harder for the molecule to have their carbon atoms get close together and almost like intertwine relative to each other. And the straighter the chain, the better. So having a straight chain hydrocarbon is better for intermolecular forces for those groups inducing a larger dipole moment. So if I imagine a second molecule on top of this straight chain structure, it's going to have a stronger force of attraction. So a branching point weakens intermolecular forces. So we saw an example before of having straight chain pentane versus having a central carbon with CH3 groups hanging off of it. The branching kind of creates a kink in the structure, makes it harder for two molecules to have a strong intermolecular force of attraction relative to each other. Okay, so branching weakens intermolecular forces, so therefore not having the branching strengthens intermolecular forces, making it take a greater temperature to separate. So think about how, and we'll see this a little bit later too, when we compare some melting point and some enthalpies of vaporization versus enthalpies of sublimation or enthalpies of fusion. As we start thinking of the enthalpies of the phase change processes, in order to boil a substance, we have to break all the intermolecular forces in the substance. So we have to overcome everything that's holding those two molecules together in order to boil it. Okay, which substance below can only exhibit the dispersion force of intermolecular attraction? So what that means is to only have a dispersion force of attraction means that the compound has to be nonpolar. So the question is asking which of the molecules below are nonpolar. So let's look at one. Let's think about this together for a minute. I think there's a question like this on the test, where if you're doing a Lewis structure, you might write your Lewis structure this way for CH2Cl2. You might put the lone pairs on the chlorines. If you double check the count of electrons, we have 20 total electrons to distribute, and we have 8 around each of the chlorines. So that's 16, and then we have 18 and 20 for the CH bonds. So all of our electrons are distributed. Now, you might have been wondering, well, if I draw the structure one of these two different ways, I might have a different answer on polarity. So if I sketch the structure this way, you might be saying, well, if I sketch it this way, it looks like it's polar. If I sketch it this way, the top version looks nonpolar. So is the molecule polar or nonpolar? What do you guys say? Who thinks it's nonpolar? Everybody thinks it's polar then? Or is afraid to answer? But the molecule is polar, and it's really because it doesn't look like either of these two structures. The real geometry is not square planar for this molecule. The real geometry for the molecule is tetrahedral. So no matter which of those two Lewis structures you want to sketch, they're both the same Lewis structure. Neither one is right or wrong. The real three-dimensional shape, though, looks like the tetrahedron, which puts the bond angle at closer to 109.5 degrees. So even if you're looking at this bond angle here, in our Lewis structure, we have to know that that's 109.5 degrees. Whether we draw it that way or just try to picture it that way in our minds, we have to know that this molecule here is really tetrahedral. So just remember, when you're sketching a Lewis structure, you're not thinking about three-dimensional shape, then think about three-dimensional shape, predict your bond angle to not be 90 degrees or 180 degrees, but really 109.5 degrees, no matter which of these two structures we're looking at. So this molecule here is certainly going to be polar, so it can't only have the dispersion force of attraction. HBr, as long as you have a bond with two different atoms, it's going to be polar. It's just a matter of how polar it's going to be. Our most electronegative atoms are NO and F, also Cl, Br, sulfur, phosphorus. Those atoms there are the next most electronegative. So this molecule here is going to have dipole-dipole forces. And so then the CH bond, I don't have to think too hard because that bond is not so polar, and also the molecule is going to have all those carbons and hydrogens opposing each other. So this molecule here is going to be the nonpolar molecule that experiences only the dispersion force. So dispersion force is the only force of attraction in nonpolar compounds, but polar compounds still have dispersion forces. So when we're thinking what intermolecular forces does a compound have, HBr would have dipole-dipole forces and dispersion. So we still have dipole-dipole and dispersion forces for both of the molecules in 1 and 2. So liquid samples of HBr or CH2Cl2, that's dichloromethane is its name, that those samples would have the dispersion force of attraction on top of the dipole-dipole force. Okay, so think about how just about every substance will have A dispersion force of attraction is just a matter if it also has dipole-dipole or hydrogen bonding forces. Do we have H bonding forces of attractions in any of those molecules in 1 through 3? Of course, 3 doesn't have it because we don't even have polarity there. So definitely not in 3. And then 1 and 2 don't have H bonds either because we need hydrogen directly bonded to NO or F. And there's no NO or F in any of those compounds. Now, there's a couple of properties that we can relate to intermolecular forces as well in terms of how the property trends with intermolecular forces. And so viscosity is a measure of resistance to flow. So substances that resist flowing would be like molasses. So molasses has a high viscosity. Just making sure we think what it means to be highly viscous is highly resistant to flowing. And so thinking about something like molasses, which does not flow readily, has a high resistance. Now, without even knowing anything about viscosity, you can probably imagine the property of a liquid that would give it resistance to flow is strong intermolecular forces. So if you have a liquid where the molecule has strong intermolecular forces with the other molecules in the liquid, it's probably going to make that liquid have a more viscous property. And then a liquid that has overall weaker intermolecular forces will likely resist flowing to a lesser extent. Now, one other detail here is it's hard to talk about resistance to flow in things like methane, because methane is a gas at room temperature. So you kind of have to have something that's a liquid at room temperature. At least if you're thinking about viscosity at room temperature, this substance has to be a liquid at room temperature. Hexane, heptane, octane, nonane, decane, these substances here are all liquids at room temperature. So at room temperature, these substances here are all in the liquid state. And so then we can think about how we go from having 6 to 7 to 8, 9 to 10 carbon atoms growing the size of the molecule. So as we go down this way here, we're increasing the molecular weight. And then we increase the intermolecular force of attraction. We're increasing the dispersion force because those are nonpolar molecules. The only force of attraction we have is that dispersion force. And the viscosities, these actually aren't very high viscosities, but you can see we get an increase of viscosity as we go from top to bottom in this trend here. So increasing in size is increasing our intermolecular force due to increasing the dispersion force, and then we get an increase in the viscosity. So the viscosity is going up with intermolecular forces. Now, if you think about, like octane, that's like gasoline, so like, or is a main component in gasoline. Gasoline flows pretty readily. There's not much of a resistance to the flow of something like octane or decane. But if you get up to even larger hydrocarbons, you get to an oil where you have like C50 compounds, there you can think oils have a much greater viscosity, much greater resistance to flowing. And again, if you think about what's in molasses, molasses has long chain sugar molecules. So imagine a glucose on a long chain. So you have long chains of hydrogen bonding molecules, yet still the substance is a liquid at room temperature, or at least in that form it's a liquid, and can therefore have a strong resistance to flowing. So a couple other properties are surface tension and then somewhat related to capillary action. And so surface tension is what's being shown in the figure here. So surface tension is related to the energy that has to be overcome to break the surface of a liquid. So insects can sort of walk on the surface of water because they're not breaking the surface. They don't apply enough energy to break the surface of water. And so the inward force that has to be broken, or the inward force that's holding the surface of the liquid together, has to be overcome in order to break the surface of the liquid. And so a liquid that has a stronger intermolecular force requires a greater energy to break the surface. And so the surface tension increases with increasing intermolecular forces. So if you have a liquid with a stronger intermolecular force, more energy has to be applied to the surface in order to break it because there's a stronger force holding those molecules together. I'm always glad when you guys made it to class. And so having a stronger intermolecular force requires more energy to break the surface. Therefore, we say that's a higher surface tension. And so water, strong intermolecular force due to hydrogen bonding gives it a relatively high surface tension. So if you made that intermolecular force of water weaker and didn't have the hydrogen bond there, you had some other type of liquid that doesn't have hydrogen bonding capabilities, not going to have as high of a surface tension. You can also think about capillary action as somewhat related to this. So if you picture like a test tube, or if you're picturing like a plant stem, what you need in order to have water flow up the plant stem or flow up the capillary tube and make a meniscus is you need there to be a mutual attractive force. So you need whatever the test tube is or the plant stem. If there's a mutual attractive force with water, then water flows up the stem because we get this like meniscus upward. And so what we need is a mutual attractive force between glass and water. We get this because glass has a bunch of SiO2 polar groups that pull in the polar water molecules, so we get an upward meniscus. And so then a plant stem also has the sort of like the sort of sugar type backbone molecules. We have hydroxyl groups on the plant stem that pull the water upward through a mutual attractive force. So what you need is mutual attraction between the plant stem or the capillary tube to get this capillary action. If you had the opposite, then this wouldn't work at all. If you had a substance that you were trying to pull up into a test tube like mercury, you actually get a downward meniscus because you get a weak repulsion between the silicates and the mercury. So the mercury atoms are actually being repelled by the glass, so you get a downward meniscus. So it's going to be pretty hard to pull mercury up a test tube or pull it up a plant stem because there's not a mutual attractive force. And so what this means here, this is showing us repulsion. So capillary action is that if we have a attraction, if we have an adhesive force, that's another word for attraction or attractive forces. So if we have an attractive force or mutually beneficial force between the test tube and the liquid, we get an upward meniscus. If we have a repulsive force, then we get a downward meniscus. And so then we call that an adhesive force. We get a cohesion versus adhesion. So the forces that hold the liquid together versus the forces that are pulling them towards the liquid. So we can say mercury has a stronger cohesion, has a stronger attractive force with itself than it does with the glass material. So we get repulsion here, we get a stronger attractive force between the mercury atoms, and so then we don't have them being pulled upward in terms of a meniscus. So we get a downward meniscus for mercury, an upward meniscus for water, and that's for water showing us capillary action, or if we think of it in like a plant stem situation, that would draw the water upward. Okay, so those are a couple properties that relate to attractive forces. So strengthening the attractive force or having a beneficial or mutual attractive force leads to this upward meniscus and capillary action. So a quick summary is that intermolecular forces have effects on properties like melting points and boiling points. And so if you increase the intermolecular force, then you increase the melting point. So we get a direct relationship between increasing intermolecular forces, you increase the melting point. Melting breaks some of the intermolecular forces between a substance. So if we increase those forces of attraction, we're going to increase our melting points. Same thing, we get a case where we have proportional boiling points increase as we increase intermolecular forces as well. So there's a direct relationship between intermolecular forces and boiling points. We saw it with viscosity just now too. If you increase strengths of intermolecular forces, you increase surface tension. Same thing with viscosity and surface tension increasing with intermolecular forces. Capillary action as well, increasing with mutual attractive forces between the substance. So if you increase those forces of attraction, you increase capillary action. And then we're also going to see that the phase change enthalpies are going to be related to intermolecular forces in the same way. If we increase these values here, the enthalpies of the phase change processes should increase. That's going to be the explanation for why the melting points and boiling points increase. So we can look at the actual magnitudes of delta H's of those phase changes, kind of taking us back to some topics out of chapter 5. And then lastly, we'll get into vapor pressure, which is for this slide here, the one property that's inverse to intermolecular forces, meaning if we increase the strengths of intermolecular forces, we're going to lower vapor pressure. So we need to look at why that's the case. So I just wanted to point out here on the slide, there's only one property that goes inverse to intermolecular forces, and that's vapor pressure. And we haven't seen why yet, but we'll get into that in a couple of slides. Let's talk about the phase change magnitudes first. The first thing that's worth pointing out is that the phase change for melting versus freezing is what we call the delta H of fusion. So if you go from solid to liquid, the phase change here is our melting or fusion process. We call the enthalpy required to go from the solid to the liquid state, we call that our delta H of fusion. You could call it the delta H of melting too. So if you think of delta H of fusion as the enthalpy required to melt a substance, that would be a fine lingo too. But usually we call it delta H of fusion is the vocabulary we tend to use. And then you can think back to hopefully chapter 5 to think about, should this be exothermic or endothermic? Should a solid have to absorb heat to melt, or does it give heat off when it melts? So what do you guys think? Absorb heat or give heat off? Should have to absorb heat. So ice, we have to take it out of the freezer so it can absorb a higher temperature. So it has to absorb heat in order to melt. And obviously the same thing, if we just change the name, it's still going to be greater than 0. And so the same thing for liquid to gas. So to go from liquid to gas, we call that the delta H of vaporization. You can think of the delta H of boiling. So to go from liquid to gas, to go from a liquid phase to a gas phase, the energy of the system has to increase, so we have to have energy absorbed as well. So this has to be greater than 0. So we have to have heat absorbed, of course, to go from liquid to the gaseous state for any substance. But if you notice, the magnitude for the solid to liquid is smaller than the liquid to gas magnitude. So why, if we call this magnitude here, let's call this X and we call this Y, why does the magnitude of X look smaller than the magnitude of Y? And that can be understood through melting breaks some of the intermolecular forces, but boiling has to break all of the remaining intermolecular forces. And so the fusion process, this breaks some of the intermolecular forces. And then this process here, this breaks all the intermolecular forces, or at least all the remaining intermolecular forces. Now you can also see the solid to gas transition. That's in the case of going directly from the solid phase to the gas phase. That process is sublimation. So we call that phase change delta H of sublimation. Of course, it has to be greater than 0 too. To go from solid to the gas phase, the substance has to absorb heat in the process. But if you notice the two magnitudes of our delta H of fusion plus our vaporization, if we take X plus Y, that would equal our delta H of sublimation. So if we take our fusion and our vaporization enthalpies and add them together, that would give us our delta H of sublimation. So if you notice, our delta H of sublimation is just our X plus Y. So whatever the delta H of sublimation is, plus the delta H of vaporization. And that comes about from Hess's law, if you think about it. It's just the energy it takes to go from solid to liquid, liquid to gas, adding these two together. So if we take these two delta H's here, add these reactions up, of course they're going to sum up to be solid to gas, liquid phase canceling, and then our delta H, again, delta H of sublimation, or delta H of fusion plus vaporization. Now, if we flip the processes, of course, we have exothermic reactions. So if you want to go from gas back to liquid, that process is condensation. And of course, you'd have the negative sign for delta H, so that'll be an exothermic process. If you want to freeze a substance, liquid to solid, negative delta H, heat has to be lost to go downward. And the same thing if we want to have a deposition reaction, solid to gas phase, that's going to be negative, of course, as well. And it would be the sum of the two negative for the condensation plus the freezing processes. So if you flip, just to show one of these, if you go from gas to liquid, that is the negative, the delta H of vaporization. So you're just flipping the sign of the vaporization enthalpy sign. So the next slide will compare some different magnitudes of enthalpies of fusion versus vaporization, and then showing the sum of the two going to the heat of sublimation. So butane, 5 for fusion, so it takes 5 kJs per mole in order to go from solid to liquid butane. It takes 24 kJs per mole to go from liquid to gaseous butane. And then if we want to go from solid to a gas directly, it's the sum of the two. So 5 plus 24 is 29. So the delta H of fusion, or excuse me, the delta H of sublimation of butane solid to butane gas, that this solid to gas direct reaction here, that delta H would be 29 kJs per mole. And so for diethyl ether, so diethyl ether now is similar formula to C4H10. We have comparable molecular weight, but we have now a polar compound. So you see these values here are higher. And this is because we now have a polar compound. So we have a higher delta H of fusion, delta H of vaporization. The sum of the two is still 36. 7 plus 29 shows us the delta H of sublimation. And then water. Now, water is not a great choice for this slide. I don't know why they didn't put something like butanol or something that's going to be closer in molecular weight to the other two. Because at first glance, you might wonder, why does water go down in terms of the delta H of fusion compared to diethyl ether? Because water, of course, is polar, but has hydrogen bonds. But water is a lot smaller. So water loses a lot of dispersion forces that the diethyl ether had. So the numbers here really aren't meant to be comparable from molecule to molecule, but water does have a pretty high enthalpy of vaporization to overcome all of its hydrogen bonds. And so we add the two together, we get 47. But notice here that the magnitudes of the delta H of fusion are a lot smaller than the magnitudes of the delta H of vaporizations. So the magnitudes of the vaporization enthalpies are always higher than fusion, just because of the difference between breaking some versus all of the remaining intermolecular forces. One that's relatively close in magnitude is mercury. So mercury has molecular bonds that are uniting the mercury atoms. So we do have from a pretty high enthalpy of fusion. I don't think I would expect you to have known the magnitude or predicted the magnitude of mercury, but we're just seeing here a high enthalpy of fusion, pretty high enthalpy of vaporization. Some of the two are its enthalpy of sublimation. Okay, so just comparing some different substances, but really seeing that the enthalpy of vaporization is a larger magnitude than the enthalpy of fusion. Now, this slide here is showing us all the phase change processes and temperature change that relate to energy transitions that have to take place in order for a substance to melt and change temperature. And so what we're showing here is, imagine you have an ice sample at minus 25 degrees C. That's our starting point here. In order for ice to melt, it has to first warm up to 0 degrees C. So ice has to change its temperature. Ice has a specific heat that's specific to the ice phase of water compared to water having a slightly different specific heat. But this here is related to a specific heat of ice. There are some numerical examples of this problem. I wouldn't get too worried about solving a math problem related to this type of diagram, but just more trying to understand that a certain amount of energy has to be absorbed to change temperature. Another thought here would be that if you add, in your freezer, you generally want the ice to be well below 0 degrees C so that you have some energy that it can pull into the ice still. So if you have ice at minus 25, it's going to keep a drink colder than the ice were at 0 degrees C to begin with. I think I mentioned this before, like our ice machines. If you have a portable ice machine, I bet how many of you guys have these in your dorm rooms? I bet a few people have them. I always notice that they don't keep water super cold. It's because they keep that ice is right at 0 degrees C. It's not at minus 25 degrees C like it is, or probably more like minus probably 20 degrees C is the normal ice temperature in an ice chest in your freezer at home. So if you had colder ice, it's going to pull it's going to have more heat it can absorb in order for it to then later go through its melting process. So in order for ice to melt, it has to go through then the phase change enthalpy process at 0 degrees C. So the idea would be that a substance well below its melting point has to raise up to its melting point, then has to go through the melting point through the absorbance of heat. You'll do this in OChem where you'll actually test the purity of compounds by actually looking at a melting point process. So they have a melting point apparatus. You put some compound into a little test tube, and then you have a little viewer microscope so you can see the sample, and then you have a heating element, and then you have a thermometer, and you're kind of watching for when specifically that sample melts so you can pick out the temperature rate where it melts. And you're also generally looking for the range at which a solid melts. If you have pure ice, you're going to see that the thermometer gets to 0 degrees C and then stays there until the substance fully melts. That the range of ice melting is pretty much 0 degrees C to 0 degrees C. Now, if you had an ice water sample, you're gonna see a wider variability here because ice, this is something you'll see in 1220. Ice will pull the freezing point down of water. It'll give you a wider range of melting points too. So instead of it melting at one specific temperature, it's gonna melt across a variety of temperatures. But the idea is a pure substance is gonna stay at 0 degrees C until it fully melts, and then the ice fully melts, and then it can warm up. If we're heating it, it's gonna then warm up to 100 degrees C, the point of the next phase change process. And then the sample is gonna wait at 100 degrees C for all the compound to vaporize into steam. And so then we have steam form. Now notice that if we're trying to vaporize an entire sample of water, the process that we're gonna be waiting for the longest is that steam formation process. Now you can imagine, like imagine you put a pot of water on the stove. The thought would be that imagine you put a pot of ice on the stove. So you put a big old bucket of ice into like a pot that you could heat on the stove. And for probably a minute or two, you're not gonna see too much. For a minute or two, you probably hear some crackling and some sounds, but you probably won't see too much liquid form for at least maybe 30 seconds or so, because the ice is just warming up at first. So it's really not gonna start melting until the ice hits that 0 degree C point. Then you're gonna see it melting, but if you had a thermometer in the ice, you're gonna see it's gonna stay right at around 0 degrees C until it all melts. Then the temperature relatively rapidly would get up to the boiling point of water. But if you then wanted to sit and watch the entire sample vaporize, you're gonna sit there for a while. So if you think of how long it takes a pot of water to boil on the stove, maybe 5 or 10 minutes depending on the stove or how much water there is. But if you want to sit there for all the water to actually evaporate, you're gonna be sitting there for another hour or two. You're gonna sit there for a while for all the water to evaporate. And that's because you gotta get through that whole phase change process. So the amount of heat you have to add is on the x-axis here. So the amount of heat that it takes to get across all these temperature changes and phase changes is shown on the x-axis. And then we can heat the steam up. If we were collecting the steam, if we had this in a sealed container, if we had like a Instant Pot or a pressure cooker that we were heating up, we would get beyond the boiling point of water and have steam at a high temperature. Okay, so the idea here is just in order to go through phase changes, you have to add heat to get to your phase change temperatures and heat to get through the phase changes. And then you have to add a lot of heat to get through the phase changes in order to change the phases of our substances. And of course, you could do this with math. We're gonna skip the boring math problems that say, well, how much heat does it take to change an object's temperature? Those problems, if you ask me, are pretty boring. They're not worth looking at. I don't think you're gonna see any of those on the exams. You might see a few on some practice quizzes. I don't think there's any on the homework sets. You might see a couple examples like that in the book, just to be aware of those. Okay, now let's get into vapor pressure. I did mention that this is the one property that goes inverse to intermolecular forces, and let's try to think about why. And so what causes vapor pressure is if we imagine something like ethanol, we add it to a flask. I can even kind of do this demo just with a cup of coffee. So like when you put a cup of coffee, you fill it and relatively have room temperature air above the coffee when you first fill a cup into a container. And then you seal the container in and you kind of shake it, and then it hisses, and you get that like hiss sound. Of course, if it's a little bit hotter, you get a more pronounced hiss. What does that hiss do to? Well, it's due to the water that's hot. So we have hot water in the container, and then when I seal it in, that hot water is vaporizing some of it into gaseous water. So I have pressure building up inside this container because there's nowhere for it to go. The pressure can increase. This is now at a constant volume. I've sealed in the container. So I have hot water that's now vaporizing into the air above it, increasing its pressure. And then the hiss is just that pressure being released when I open the container. And the same thing can happen if I take something like ethanol, I fill it into a flask. And so when the moment I add the ethanol to the flask doesn't have any ethanol vapors in it. But ethanol does have a vapor pressure. If you've never smelled ethanol, that's probably good. But if you've ever smelled a bottle of vodka or something, you know that ethanol does have an odor. The odor is, of course, due to its vapors. And so when we add ethanol to the flask, eventually the vapors are going to fill the flask until they hit the point at which the vapors are equal to the vapor pressure of ethanol. And so ethanol at any temperature has a vapor pressure. And so the partial pressure of ethanol reaches the point where it's at its vapor pressure at that temperature. Now, this is something that's going to take us a little bit in a couple slides to maybe understand, but you can probably appreciate that if we increase the temperature of ethanol, that you'd probably smell more ethanol vapor. That if you just had a little bit of a warmer ethanol sample, now don't go test this at home, because if you put a flame to ethanol, it can ignite. So don't play around with this. But if you increase the temperature of ethanol, you would probably smell more vapors or expect it to be more vaporous, because it's going to give off more vapors. Why would that be the case? Well, it's probably the case that giving ethanol more energy allows more molecules to escape into the vapor phase. So as temperature increases, we should have an increase in our vapor pressure. So that's one property we can relate, that if we can increase the temperature of this sample here, we're going to have more molecules enter the gas phase. Now, another thing you don't want to do with a glass sample is generally test this hypothesis either, because if you have a gas sample that's a sealed container and you start heating it up, it could blow up. So again, don't go play around with this at home. I don't want you to think you can pressurize if you have glassware at home from maybe like a chemistry kit or something. I don't want you to necessarily think, oh, we can pressurize the sample and see what happens. It could blow up. So don't necessarily test this hypothesis. But so increasing our temperature should increase our vapor pressure, put more molecules into the gas phase. And so now, if we're then comparing ethanol with a different substance, if we're comparing ethanol with maybe something like diethyl ether, some sort of substance that has a weaker intermolecular force of attraction, maybe doesn't have the hydrogen bonding strength, but is of relatively, say, comparable size. If we put that substance into a flask, do we think it's going to give off more or less vapors? Do we think strengthening intermolecular forces of the liquid will allow more molecules to escape into the gas phase or less? If I strengthen my intermolecular force here, if I have stronger intermolecular forces, that should weaken and lower our vapor pressure. Now, why would that be the case? It should be the case because intermolecular forces are what's holding the liquid together. And if I weaken the force, I want to weaken that force to put more molecules into the gas phase. So if escaping into the gas phase means I've overcome the intermolecular attraction of the liquid, I can overcome that attraction easier if the intermolecular forces are weaker. Now, by corollary, if I strengthen the intermolecular force, if I have a liquid that has stronger intermolecular forces, maybe like ethylene glycol, have that second hydroxyl group here, that compound we were looking at earlier, similar to ethanol, we have the second hydroxyl group, relatively comparably sized too, but the key for ethylene glycol is a stronger intermolecular force should have a lower vapor pressure. So if we can strengthen our intermolecular forces of attraction, then we should lower our vapor pressure. So that's that inverse relationship. So vapor pressure is due to molecules escaping the liquid. Molecules can escape the liquid more readily if those intermolecular forces are weaker. And so again, weaker intermolecular forces gives us a greater vapor pressure. So another thought of vapor pressure versus temperature could be this analogy here from a chapter 10 perspective that we can think of. Now we're using this slide to think of the velocity distribution of molecules in the liquid phase. So imagine the molecules in the liquid tumbling around each other. They're not going to have as high of velocities as a gas sample would have, but you can imagine at a lower temperature, the water molecules have a lower average set of velocities, and at a higher temperature, those velocities are a little bit higher. And then there's some point at which the kinetic energy needed to overcome to break that surface tension of the liquids overcome. So there's some kinetic energy those molecules have to reach, and they can break the surface of the liquid. And so at a higher temperature, we're going to have more molecules that have the ability to break the surface of the liquid, leading to, at high temperatures, a higher vapor pressure. So vapor pressure is due to molecules escaping the liquid phase. It's due to them breaking that attractive force that the liquid's holding them in by. And then by having a higher temperature gives a higher fraction of molecules with that energy to overcome the surface. So just vapor pressure versus temperature. As we increase temperature, we're going to increase vapor pressure. So that's the main conclusion from this slide, or this thought, is just showing us again another picture of how we can relate temperature to vapor pressure. Now this slide here is comparing a variety of substances' vapor pressures versus temperatures. So let's actually look at water first. And so water, we know boils at 100 degrees C, but let's think about what that means. What does it mean to boil at 100 degrees C? So like if we had a liquid sample, if we had water, like atmospheric pressure is what's holding that water together. You can think water has some attractive force. Gravity is acting as a force as well. If we weaken that force holding water molecules together such that now the force of attraction of the vapor pressure of water goes beyond atmospheric pressure, then water is going to boil. So the vapor pressure, if we look at vapor pressure versus temperature, when water is very cold, so 0 degrees C, not much vapor pressure of water. If we get to about 20 degrees C, water does have some vapor pressure. In terms of torr, it's probably about 20 torr. So let's say this value here is probably a vapor pressure of around 20 torr, and that's 20 millimeters of mercury. And remember, that's 20 out of 760, so 20 divided by 760, that would be the number of ATM. So well below 1 ATM would be the vapor pressure at low temperatures. But as we start heating water, the vapor pressure is increasing. So if we get to water at probably about 65 degrees C, it has a vapor pressure of 200 torr, 200 millimeters of mercury. And so this is probably about 65 degrees here. We keep heating water. Eventually at 100 degrees C, it gets to 760 torr. Now, why 760 torr at 100 degrees C? Well, if you go above 100 degrees C, then the vapor pressure of water, the pressure that's kind of like that water wants to have, goes beyond the atmospheric pressure holding it together. And so atmospheric pressure is what's holding water together. If water then has a vapor pressure beyond atmospheric pressure, it boils. And so if this is our standard pressure, then 100 degrees C is our normal boiling point. So the quote unquote word normal, I'm so bad at writing. Normal boiling point means the boiling point at standard atmospheric pressure. So a lot of times we just say boiling point of water is 100 degrees C, but what we really mean is that the normal boiling point of water is the boiling point at standard atmospheric pressure. Of 1 ATM or 760 torr. So our normal boiling point is just defined as the point at which a liquid has a vapor pressure of 760 torr, because 760 torr is the pressure the atmosphere is holding that liquid in by. So as soon as the pressure goes, the vapor pressure goes above that value, the liquid starts boiling so it can escape into the atmosphere. So it can escape into atmospheric pressure. And so if you notice, ethanol's boiling point, 78.3 degrees C. So that's the point at which ethanol has a vapor pressure of 760 torr. So if you go below 78 degrees C, then ethanol has a lower vapor pressure. And so then, like ethanol versus water, it's kind of hard to compare. If I just said predict ethanol versus water's boiling point, I think you'd have a hard time because ethanol is bigger due to the CH3-CH2 chain, so it's a higher molecular weight. It only has one hydrogen bonding site, but ends up having a slightly lower boiling point. But if you knew it had a lower boiling point, then you would know that it would reach that 760 torr at a lower pressure. So it's reaching 760 torr at its boiling point. And diethyl ether, which is a compound that doesn't have any hydrogen bonding ability, has a much lower boiling point compared to those two molecules. So lowering the boiling points due to weakening intermolecular forces shows that we're getting to the 760 vapor pressure at a lower temperature. If we then compare to ethylene glycol, that's that second hydroxyl group on to ethanol, so it's like ethanol with the second hydroxyl group, much lower vapor pressures altogether. So we're not going to get to the boiling point of ethanol until around 200 degrees C. So much higher boiling point and really no vapors at all at low temperatures. So ethylene glycol, useful as antifreeze because it doesn't have much of a vapor pressure and then has a much higher boiling point. Okay, now one other detail to mention is what if we change atmospheric pressure? And so we can't really change atmospheric pressure, but what if we change the surrounding pressure? So we can do this with a vacuum system. So imagine I have a liquid and I put it onto a sealed system with a vacuum pump reducing the pressure. So there's now less pressure holding that liquid in by. So let's say I connect a sample to a vacuum system that has a 200 torr pressure. So if I use a vacuum pump to reduce the pressure of my system down to 200 torr, so this is my surrounding pressure onto a system, maybe you could be using a pump or something to reduce the pressure to get down to this pressure, then my diethyl ether boils at 0 degrees C. Ethanol, closer to probably 45 degrees C. Water would boil at around 65 degrees C. So we can change boiling points if we change the surrounding pressure, either through changing the atmospheric pressure, probably harder to change that, than to just put a sample onto a vacuum system where we use a vacuum to lower the pressure. So it's commonly done in labs that if you use a system that can lower the pressure, you can lower your boiling point so you don't have to heat up a distillation process or a process of boiling a substance. You don't have to heat it up as high. Now, a pressure cooker does the opposite. So a pressure cooker, like an Instant Pot is a pressure cooker. Maybe it's not built as such, but it's really just a system that's a sealed system that can increase its pressure. Because if our surrounding pressure now goes above room temperature, we then increase the boiling point of water. So an Instant Pot cooks things faster because instead of cooking food at 100 degrees C at the boiling point of water, you can cook things at more like 110 or 120 degrees C because you've now increased the pressure due to the system that you're using to heat your food. And so a pressure cooker can increase our boiling points because they're increasing that surrounding pressure. And then one other detail is if you're like in the mountains, you could be in this region here. So if you're just at high elevation, if you've ever noticed, most food has like cooking instructions for at high altitude. At high altitudes, atmospheric pressure is lower, and so water is going to boil at a lower temperature. So if your water is boiling at 90 degrees C instead of 100 degrees C, it's going to take longer for spaghetti to cook. So food's going to take longer to cook at high elevation, so hence cooking times tend to be longer. Okay, so with that, we will get into this example next time and a couple of other examples relating to phase diagrams. Then we'll be through chapter 11 into chapter 12 next time. Quick little demo to do for today. So this, you guys are going to the football games this Saturday. Everybody comes back after Thanksgiving. Do the football game. Let's do the football game at least. All right, so this is our here. Okay, so if you're at the game, or even if you're just watching on TV, it's at home, so when we see that team come up north, what are you going to do when you see these colors in the stadium? Ooh. But now, what's going to happen on the field is hopefully the same thing that can happen with chemistry. So let's see if we can beat that team from up north. So all it takes a little chemistry, guys. All right, so let's have a fun week. It's Beat Michigan week or Beat That Team Up North week. Hopefully, if you see any M's, you cross them out with some red tape this week. And then if you're going to the game, have fun. And I'll see you guys after Thanksgiving. So have a great break.